Uh, Good morning, everyone. I'm Ritabrata, a graduate student here at ICTS with Professor Rama Govindarajan. This work has been done in collaboration with Arjun Sharma, who was a scientist here in ICTS, and I'm a graduate student in Cornell. So, by the end of this talk, I will try to motivate and hopefully discuss with people who are really unfamiliar with the transient growths in fluid flows and the optimal structures for such transient growths. And I'll try to go slow as I'll try to discuss more about the methodology that's involved in calculation of these optimal structures. So starting from a very basic equation, let's say you have a dynamical system which is evolved by which evolves according to a matrix. It's denoted by M here. So depending on the quality of the matrix, which I'll define in a short while, this dynamical system can take different properties, sometimes very interesting. So one of the property of this matrix is the commutator of the matrix and its transpose. If it's zero, the matrix is called a normal matrix. If it's non-zero, it's called the matrix M is called a non-normal matrix. And the condition of non-normality is mathematically this one. So when the matrix M is not normal, like it's not normal, then simple eigenvalue analysis doesn't really give you all the information regarding the system. As is shown here, I start with two initial conditions of my choice, and the matrix M has, let's say the matrix M has two negative eigenvalues, and all the initial conditions will die down at longer time limits. But when you look at the combination of these two vectors, the resultant slightly grows, like is seen as a hump here in short times. So this really eluded researchers in fluid mechanics for a big period of time, and this was termed as like this could only be understood by non-modal analysis. Like you cannot really understand the system mode by mode, but a combination of different modes, and hence this was termed stability without eigenvalues. And then the short time energy growth that happens in the system is called the transient growth. So in real life fluid flow systems, this also happens. On the left, I have systems which have the dynamical the matrix that evolves the system being normal, and on the right hand side are the cases for which the evolution matrix is not normal. So the Rayleigh-Bénard convection and Taylor-Kuwait flows are the systems of examples of normal systems, and for non-normal systems we have like your regular Kuwait flow, plane channel, and your pi flows. These are not, it's not an exhaustive list though. The common thing that you might have already guessed in non-normal system is that there is shear in the system, and shear introduces non-normality in the system, by which and because of this non-normality, the eigenvectors are not orthogonal to each other. So even when we have two decaying eigenvectors, the resultant can grow in short times. So to get to the goal of my talk, I'll just change gears and say that there has been an idea recently to understand the flow as from a dynamical systems point of view. So this this assumes the whole flow as a full dynamical system, and the flow state evolves as a trajectory in this phase space, and that trajectory is populated by various invariant sets which are exact solutions of the Navier-Stokes, and they have a stable and an unstable manifold across each of these exact solutions. And if you want to really take out a state from one stable state to another, or you really want to trigger instability, you have to give a finite amplitude perturbation to it such that it breaks the stable manifold, the energy hypersphere that is around that stable fixed point, and it has to go out of that stable fixed point to make a transition to some other state, or have like it's either transition or an slash instability. And this really isn't a self-consistent tool to understand fluid systems, and hence there is there's an effort to combine this with the linear non-modal theory that I described in the first few slides of my talk. One of the technique by which you can do that is called an adjoint looping technique, or adjoint analysis, adjoint sensitivity technique. It comes by various names. In the next 2 or 3 slides, I will show you the methodology to develop this methodology that goes in developing this adjoint looping technique and application to the real life, like Navier-Stokes equation. You can apply it to anything. Like as we are interested in fluid systems, we'll work with Navier-Stokes equation. Given by the momentum, you have the momentum, the force balance equations, the incompressibility condition. You can put as many equations as you want, like as many scalars as you want. Then you define a cost function which is of your choice, and like you are at liberty to define anything that you want. Here I define it as a combination of different things, like ratio of your initial energy, the ratio of your final energy to the initial energy, or a time integrated energy of the flow. And then once you have a cost function, you define a Lagrangian. So this Lagrangian is a combination of the cost function, which is constrained by the flow equation. In this case, you have the Navier-Stokes equation, the temperature equation, and the initial conditions of velocity and temperature, and also the incompressibility condition, and the total initial energy. And these are done with the help of these variables, which are in red. These are Lagrange multipliers, and these are also the adjoint variables. So the initial energy is enforced by a Lagrange multiplier C. This is special because an imposition of initial energy and velocity by V0I, this variable, does not really ensure that you have enforced total initial energy. So once you have formed the Lagrangian, you take derivatives of this Lagrangian with respect to all the unknowns in this equation. And when you take the derivative, if you want to reach optimality, you have to have the gradient of the Lagrangian with respect to everything to 0. Everything should, all the gradients should go to 0. Once you do that, which I'll not show the calculations, but once you do that, you get out the equations for the evolution of this variable, the adjoint initial conditions of temperature and velocity. And this one has a slightly separate issue, but I'll not go into details. So once you have that, you can follow this kind of a loop. You guess an initial condition. So I'll tell you the primary motive of this chart, of this flow chart, is to find out an optimal initial condition that does something. But what it does is defined by this cost function. You can define anything like energy, dissipation, anisotropy, your potential energy, whatever. So it's up to you. You guess an initial condition. It will be an absolutely random initial condition. You integrate forwards in time. In this case, you have the Navier-Stokes equation, and you get the adjoint variables at the final time. So you're free to choose this capital T. Then you integrate backwards in time from capital T to 0. It is because when you derive the adjoint Navier-Stokes equation, you have the diffusion term as positive. You cannot integrate forward that equation. So you have to come back in time. And then you calculate the gradient of the Lagrangian that you have defined. It's up to you. Defined with respect to the initial condition. It really gives you a sensitivity kind of thing. So how much the gradient changes with respect to initial condition. If it's 0, you have reached an optimal condition. Because everything has to identically go to 0 at optimality, or numerically, like to machine precision. If not 0, you apply a steepest gradient method, by which I mean, like, not really only steepest descent, or probably a conjugate gradient method, or whatever any sophisticated method that you want to apply. And then you do this loop again, and you keep on doing this loop, and you will at some point or in after few iterations, depending on your initial energy and many other parameters, you will come to an optimal condition. So the we really do it in a we do it in a computer, like a three-dimensional channel flow solver, which is solved in the vertical direction as in like finite difference and spectral direction in other two. From this slide, I really want to convey that this is a method that works. On the left and the right hand side, you see different kinds of perturbations, the V and W velocities. And on the top panels are the ones that you start with. These are absolutely random noise, like you start with anything. As you can see, these are random. And as you go, like iterate more and more, when you reach like this, like 20th iteration, you see these random noise have converged to structures which are like coherent structures, and they fill. And what you are really seeing are like streamwise vortices, and these are slices at a certain point in the channel. If you look at the full 3D channel, this looks something like this. Like these streamwise vortices fill the whole channel. There were some talks before my talk, which talked about streamwise vortices, optimality, and so this was for maximizing integrated energy. So how much? So the energy integrated over 0 to capital T. Here I have chosen capital T as 5. It's your choice. You can choose anything. And on the top left, you see that the convergence of the routine, where the objective function has plateaued to a constant value, and the delta objective has fallen by 4 orders of magnitude. Where delta objective means difference in the objective function before, like one step ahead of the final step. And when you change I told you we can change the optimization cost function. I changed the cost function. Now I'm maximizing for the final time energy, and this is this shows. So the one on the previous slide and this slide are for exactly same parameters, except that I'm optimizing for different thing. And as you can see, when you optimize for different thing, you get obviously you get different structures. These are 2 rows of counter rotating vortices, and what you see in color are the isosurfaces of the streamwise velocities. 40% of the streamwise velocity. And also the convergence is slightly better in this case as compared to the other one. We don't understand why. And also for different time horizons, you can get different structures. Like the colors don't really mean anything, but just to differentiate that for t equal to 10, you get stronger structures. For t equal to 5, you get slightly weaker structures. These are again 40% isosurfaces of streamwise velocity. So to summarize, shear flows only admit transient growths in any quantity, not really energy only. And the optimal structures for the transient growth are organized structures, as have been mentioned in talks before me. And as you have seen, these are structures which are streamwise vortices aligned in the streamwise direction, and they could be rows of structures, or they could be single row of streamwise vortices. And we have plans to expand it, like to do other kinds of simulations and to go to different parameter space. Yeah, that's it. Thank you.
So any question? Just a time for one question.
This flow that you considered, does it admit model growth? This flow that you're it's a flow in a channel flow, right?
Yeah, it's a channel flow. So it's a shear driven, it's a pressure driven channel flow, 3D channel. So it can admit everything, like modal, and so it can admit modal growth. Yeah. So once you are in, so it's unstable above 5772.
So your Reynolds number, what
these are 500 Reynolds number.
Okay, so there is no modal growth possible.
So there cannot be modal growth there cannot be linear instability below 5772. So if you say by modal growth, I presume you're talking about linear instability.
Exponential.
Yeah, I mean it's above 5772 only. So at 500 Reynolds number, everything should decay, but the combination would increase in short time. That is what transient growth would be.
Okay.
But above 5772, below 5772, there cannot be any instability.
And this is 500.
500.
Okay.
Just with Ritabrata during the tea break and all. So